All right. So the last thing we're going to talk about before the quiz would be the cases where you have even powers. It's not, it's not crazy. It's just, there's just more rules. And so for some of us, that may be crazy. It's like, oh, yet another rule. This sucks. Yeah, well, that's one of those things. It's like pre-calc when I was a student was the most pointless course that I could ever be sitting in until I was sitting in calculus, and when I realized, oh, that was a pretty important course. But I had the luxury of doing it. I took kind of a non-traditional approach. Did pre-calc and calculus in high school. So I got my learning experience out of the way there. Whereas like I had the aha moment sitting in calculus, man, I should have paid attention in pre-calc. And then when I got to college, I had the philosophy for math and science, you start off taking the lowest level of math that they'll give you college credit for and start from there and just keep going. Right? For me, it never stopped. So 22 math courses later, I maybe built up too much of a head of steam. But it was like, well, they'll give me college credit for pre-calc. It only counted as an elective. It wouldn't count towards my major, but I still took it. And then I was able to really kind of refine my understanding of pre-calc, and then it was off to the races. Now, we're sitting in Calc 2, so what does that mean? It means that ship has sailed. But, you know, if you reflect back upon your time in pre-calc, you either are looking back at somebody who took it seriously and worked really hard, and this stuff is making perfect sense, or you're reflecting back upon a person who is like, oh, what the hell is this stuff for? I'm not even going to pay attention. I'll just wing it on the test, and all this stuff is like black magic, you know. So your biggest review might be pre-calc, not even the calc stuff. All right. So I'll talk to you for a second about where these formulas came from. Not quite the origin story of the Pythagorean identities. I'll actually just start off with a very popular formula from pre-calc, which is cosine of 2x. There's actually 3 variations of this formula, but I'm only going to focus on 2 of them. One of them is 2 cosine squared x minus 1. Right? So what happened here is somebody along the way, and honestly, I think this, before I was talking about the integral of secant and how I'm not smart enough to come up with that one. I think this one I'm probably smart enough to come up with, because I would say, all right, I need a rule that's going to allow me to replace a cosine squared with something simpler. All right, and by simpler I mean something raised to a lower power. All right, this will do it, because if I add 1 to both sides, I get 1 plus cosine 2x equals 2 cosine squared x, and then divide both sides by 2. I get cosine. I get one of those rules that's off the page right now, but you can see it on your pages. 1 plus cosine 2x over 2. But I'll take it a step further. Cosine squared x, I want to write that as actually 1/2 plus 1/2 cosine 2x. If I had a choice between trying to integrate cosine squared x or its equivalent expression of 1/2 plus 1/2 cosine 2x, I'm going with this every single time, because this doesn't even involve complicated u substitution. If I were using u substitution on this, it would only relate to the 2x here. I call that baby u sub, because you could do that on the fly. All right? So there's really nothing to it. But this, you'd be in a spot. Like, what are you going to do with that? There's really nothing you can do. There's no u substitution for just the cosine squared x. But by using a pre-calc substitution, you get it into a form that's actually pretty easy to anti-differentiate. All right? The other variation is cosine 2x is equal to 1 minus 2 sine squared x. All right, so through all the same black magic, what we get is that sine squared x is equal to 1 minus cosine 2x over 2. But again, take it the next step and say instead that sine squared x is equal to 1/2 minus 1/2 cosine 2x. Bless you. So we have a little bit of familiarity here in that, one, they're based off of formulas that we know, but also the two formulas, the two substitutions related to cosine squared and sine squared are not dissimilar from one another too much, because one just has a plus sign and one has a minus sign, right? So as long as you can keep that straight, you're in good shape. So basically, if you know one, you know the other. So what that does is it allows us to evaluate situations where the power of a sine or cosine function is even, right? Because really, when you're dealing with any kind of even power, it's to the second power multiply. Let's say you had something raised to the sixth power. It's to the second power cubed, but it's always to the second power in some capacity. All right. So I can make my substitution here and replace the sine squared of 3x, so a little bit of an adjustment here, with a 1/2 minus 1/2 cosine, well, it's not going to be 2x, because the relationship here is that if it were x, it would be 2x, but this is 3x, so this should be what? 6x. Yeah, we gotta multiply it by 3. All right. But then for the cosine part of it, it's the same deal, just with a plus sign. So 1/2 plus 1/2 cosine of 6x. So ever so slight adjustment here. All right. So you look at that and say, well, okay, that was so helpful. What did that do? It just, out of the frying pan into the fire. It just made the situation a bazillion times worse. But we have conjugates here, right? Two binomials, one with a minus sign, one with a plus sign. When you distribute it out, and you're like, distribute this out, it's going to be a nightmare. But the outer and inner terms are going to cancel. That's what happens when you multiply conjugates. All right, if I were to use the FOIL process, the first values multiply to give me a quarter. The outer values would give me positive 1/4 cosine 6x, but then the inner ones would give me negative 1/4 cosine 6x. Cancels out. So then I just multiply the last values. 1/4 cosine squared 6x. Minus cosine squared 6x. All right. So again, you might look at it and say, situation has not improved. But I would disagree with that, because here we had both sine and cosine raised to the second power. So we had a 4th degree equation here. All right. So the power, the degree of an equation or an expression is related to the highest power that makes up that expression. All right. So you multiply the two factors together, you're going to add the exponents, you're going to get a power of 4. But here I'm getting a power of 2. So I just reduced the power of this by a factor of 2, which is great. I just got to go a little bit further, because I still have a cosine raised to the second power. So let me apply this substitution a second time. So I'm going to have 1/4 minus 1/4 times, what am I going to replace cosine squared 6x with? Yeah, 1/2 plus 1/2 cosine 12x. So a little distributive property. I mean, you have to do some math. But the idea is that you can do the math now. It's doable. Before it wasn't. All right, so we're going to have the antiderivative of 1/4 minus 1/8 minus 1/8 cosine 12x dx. You can combine some terms. All right, so we're looking at 1/8, because it's 2/8 minus 1/8, minus 1/8 cosine 12x dx. And then we're pretty much there. We just actually, I mean, you look at this and say, well, what do you mean we're pretty much there? We still have to anti-differentiate. All we've been doing is a substitution in algebra and cleaning it up. If you do all the substitution, algebra, and cleaning up, then the antiderivative part should become easy. All right, when we did the u substitution, we selected the proper u. We put all the values in. We cleaned it up. We simplified. When you actually got to the part where you had to find an antiderivative, it was nothing. Increase the exponent by 1, divide by the new exponent. Right? Here it's a little bit different, but it's still not going to be that bad. All right? We do all of this so that this becomes easy. All right? Now you could use u substitution here, but I mentioned before that what I like to call baby u substitution is the way to go. All right? Now the 1/8, that first 1/8, that's a constant. That's going to anti-differentiate to 1/8 x. All right? We'll take care of the other part here in a sec. So what you're going to do, whenever your trig function is only off by a constant multiple, you really don't have to do u substitution. You could define u as u equals 12x and go through the whole process. That's perfectly fine. There's nothing wrong with that. You just do the work on the side, you squeeze it in, and it's perfectly fine. And you know, on a test, I might even consider doing it that way, only because I don't want to take a chance of screwing something up. But what you could do is say, all right, well, I know that the antiderivative of cosine in general is equal to sine. All right, so I'm just going to pop that there. All right, now it's not sine of x, it's sine of 12x. So I'll put a 12x there. And then you kind of play the what if game. All right, you would say, all right, well, what if this were the antiderivative? I mean, I could just leave it like that. It would be ridiculous because I don't have a plus c, I don't have a sign in between. But let's just say that I thought that this was the antiderivative. I would check it by taking its derivative, right? When I do that, I would get cosine of 12x times 12. All right, so that's a problem. I don't want a 12. I want it to be negative. And I need there to be a 1/8. All right, so all I did was I built the coefficient into what I needed it to be in order to correct for what I was going to get when I took the derivative. So I made the assumption that, well, it had to involve a sine of 12x, all right? The derivative of sine x is 12 cosine 12x. Well, I don't want the 12, so that goes in the denominator. I need the negative 1/8, so that comes in, and there you have it. All right? So you're just building the coefficients. Now, if you don't like that, and you don't have to like it, because my brain works in mysterious ways, so it's not for everyone, but if you do like it, go for it. If you don't like it, then use substitutions there for you. It's a little bit more work. And it's not even a lot more work. I call it baby u substitution, baby u sub, because it's not like a lengthy u substitution approach. If you were to do it out, it'd be a couple of steps, right? But you could do it on the fly. So the way we can avoid baby u sub is to do u sub on the fly, which is basically the autocorrect as you go on, right, through the process. But I leave it up to you, right? You can't go wrong if you use one of those two strategies. All right, so I'm going to put a star on number 4. I like to do my stars in red. I don't know why I did it in purple there. A little simpler in the setup for number 4, but you know it's got the same kind of intricacies as number 3. So you know you're gonna need to take some time. So we were looking at an even power. If it were an odd power, then it's a different story. But with an even power, I'm gonna write it differently. I want to take advantage of our rules for cosine squared. All right, so I'm going to write this as cosine squared x squared dx. All right, because I have a substitution. I don't have a substitution for cosine to the 4th, but I do have a substitution for cosine squared. All right, so we'd be looking at 1/2 plus 1/2 cosine 2x. All right, that's the simplified form of it. It's a more convenient form. All right, it's just we have to do something with this, kind of along the same lines as the previous one. We actually have to distribute this out. So we're looking at 1/4. The outer and inner terms are going to multiply each to 1/4 cosine 2x. A 4th plus a 4th would be 1/2. And then plus 1/4 cosine squared 2x dx. All right. If you have a trig function that's not raised to a power, it's just a rule. All right, so that's when you start looking to your note card. Find a rule that corresponds with that. When it is raised to a power, you got to do something with it. All right, it's a substitution and then a rule. All right, in this case, the 1/4 and the 1/2 cosine 2x, they're ready to rock and roll. It's the cosine squared 2x. I have to make an adjustment. I have to handle that. All right, so I basically have to apply the rule that got me from cosine squared of x to 1/2 plus 1/2 cosine 2x. I have to apply that rule a second time. All right, so you know, not something you're looking forward to, but it's something that you can do. All right, so just doesn't mean you want to do it, but you can do it. All right, so 1/4 plus 1/2 cosine 2x plus another 1/4 and then I'm going to swap out the cosine squared 2x for a 1/2 plus 1/2 cosine of what? What do we say? 4x, yeah. Again, it's like familiarize yourself with the rules, because this is one of those things where if you don't know enough to know when to look at a formula sheet or a note card, it doesn't do you much good. All right. A little algebra. I'm going to distribute the 1/4. Can't wait to see all the remind messages about not enough space for this problem for typo bonus. And the previous one I gave someone today, I forget who. But spacing is always a concern, because again, here's my spacing. I can always fit it, right? So if you can't fit it and you write at a reasonable size, I mean, I had people that wrote I mean, their letters are the size of like entire sheets of paper. I'm like, like you I'm not listening to. Like you write huge, it doesn't count. But if it's someone else, like if you write it at a reasonable size and you're not able to fit it in there, that's typo bonus. So get it in. All right, so 1/8 cosine 4x. All right, combine some like terms. We don't really have much to combine here. So 1/4 is the same as 2/8, so 2/8 plus 1/8 is 3/8, plus 1/2 cosine 2x, plus 1/8 cosine 4x dx. Now again, this always happens to somebody, and again, I don't want it to be a self-fulfilling prophecy, but people do all this work, they get to this point, and then they just move on to the next question on a test. Like, aha, I did it. Felt like I came a long way. Like, yeah, but you didn't actually find the antiderivative. So do the next step. All right, so very important. 3/8 x plus antiderivative of sine, cosine is sine. I just stole my own thunder there. So it would be sine of 2x. But again, this is what I was talking about last class. Instead of doing u substitution, just to account for like a little measly 2x, just kind of play it out. If I were to find the derivative of sine of 2x, it would become cosine 2x times 2. All right. Well, I don't want a 2, I want a 1/2. How do I make a 2 into a 1/2? Divide it by 4. All right. So 2/4. What did I say? Yeah, divide the 1 by 4. So 1/4. 2/4 would become the 1/2. All right. I confused myself there for a sec. All right. Antiderivative of cosine again is sine. Sine of, I don't need the parentheses there. 2x, 4x. Now it's a snowball effect here. The derivative of, if I'm checking, the derivative of sine of 4x would become sine of 4x times 4. Right? I don't want a 4, I want a 1/8. To get from a 4 to a 1/8, I divide by what? Say it again? 32. So 1/32. All right. What a lot of people do is, instead of doing it that way, they just say, okay, I'm taking the antiderivative of this, I just divide by the derivative of the thing on the inside. That only works if the derivative of your inner function is constant. All right. If this were something like x squared, all bets are off. You'd have to use u substitution. But if it's a linear function within a trig function, you're really just dividing the coefficient by the derivative of the linear function, the slope of the linear function on the inside of the trig function. All right. So little shortcuts. If you got a few minutes on your hands during a test, worst case scenario, let u equal 2x. Go through the process. Let u equal 4x. Go through the process and see where it gets you. All right. If you got the time, then take advantage of it. All right. Trial and error for simple functions is never a bad thing. It's when you're dealing with something like on that previous page, the e to the negative 4 over 5x. You don't want to be guessing what the final answer is and checking it by taking the derivative. Something like this, I don't see why you can't, or at least for that component of it. Expected to know it, so. But this is a product of two trig functions, and so sometimes the sum and product identities from PreCalc can be helpful. It's just these are formulas that are really kind of out there. I mean, I don't know how many people would have thought, and I put myself in this category, just like I said this before, the idea that I'm smart enough to understand when other people come up with these rules. I'm not always smart enough to understand how I would create this rule myself if I needed to. All right? To think of taking the average of the sum and difference identities for sine and cosine, and then that generates a rule. Like that's not me. I wouldn't have come up with that. All right, unless I was like a billionaire again with a lot of time on my hands. And with that in mind, that time. Like I've lived my life. I've done everything that I could have possibly wanted to do. And I have literally nothing else to do. Like I have lived every ounce of life. And now it's like, okay, well, I did it, you know? I went to the moon. I cured a disease that was incurable. Like I got nothing else to do. All right. Well, let me invent some math now. You know, that's where we're at. All right. I think this falls into that category. So anyway, what's happening here is all you're doing is finding the rule that corresponds to this integral. Sine times cosine. All right. Well, that's the first rule. So here's my A, and here's my B. This rule is telling us that we can expand out, instead of writing sine A cosine B, I could write 1/2 times the sine of A minus B plus the sine of A plus B dx. I mean, it's a pretty cool rule, but it's a very, very specific rule and works under very, very specific circumstances. I mean, in all honesty, a rule is good if it takes you from something you can't anti-differentiate into something you can. So that can't be a bad thing. It's just, I never would have thought to do this. And so if you're wondering why, I'm sure you're all dying to know this, why this kind of question wouldn't be on the test. If it's not something I would think to do, I wouldn't expect you to think to do it. All right, so sine of x plus sine of 9x. Distribute if you want, or pull out the 1/2. I like to distribute. I've gone over that. Just because I'm always fearful that I'm going to lose my coefficient, so I keep it as part of the party. And so this is just an extension of the same idea of the last question. Anti-differentiate, well, the first part's easy because the antiderivative of sine is negative cosine, so negative cosine of x, but we have the 1/2 there. There's no coefficient in front of the x, so we're good to go. Plus, for the second one, again, antiderivative of sine is negative cosine, so actually let me change this to a minus. So it'd be negative cosine 9x, but then I'm going to divide that 1/2 by a 9. So 1/18 plus c. All right. So whether you're reasoning it out and saying, well, negative cosine of 9x would have a derivative of sine of 9x times 9. I want to make that 9 into a 1/2 divided by 18. Or what I was talking about before, just take your coefficient and divide it by the slope within the trig function. Either way, you're going to get that negative 1/18. All right. You know, the act of taking the antiderivative is not hard here. It's just that first step. And I'll tell you, I mean, I have given this problem before, like as on a quiz test, and it almost always is either left blank or completed with nonsensical work, because people start grasping. They're like, well, I'll try to get some partial credit. I have no idea what the hell to do, because you don't instinctively think to look for a rule for something like that. All right. Generally, what ends up happening is people take the cosine of 4x and make it 1 minus sine of 4x. That's not even remotely correct. That only works for powers of 2. All right, so Pythagorean identities only work if you're raised to a power of 2. All right, so delving into the world of secants and tangents. That's what I'm saying. Now, when we're looking at, I mean, it's right now we'll look at integrals of the form of this and that. The reason we're looking at it in this form is because if you have a secant multiplied by a tangent, it's going to fit in some capacity the secant tangent rule. The antiderivative of secant tangent is what?
Secant squared x. Secant squared.
Just the secant. Yeah, so it's the right idea, you know, like you're in the neighborhood and that's worth something. So if I had the antiderivative of secant squared, what would I be looking at? The antiderivative of secant squared is tangent. Right? So that's where this idea is coming from. Can I say the secant squared? Can I say the secant times tangent? Because I know what those antiderivatives are. Everything else I'm going to want to try to cancel out in some way, shape, or form. So it's really take a shot, see what happens. Here you look at it and say, well, without too much effort, I can definitely save a secant tangent. Now it's just a question of whether that's the right way to go. All right, but I can't save something that isn't there, right? I see a secant. How could I save a secant squared? Well, there is a relationship between tangents and secants, but I don't want to force anything. I'm going to go for the obvious thing. Horse, not zebra. So secant x tangent x times tangent to the fourth of x dx. So then you stare at it for 15, 20 minutes and then hope for divine intervention, and it doesn't come. And then you start grasping at things. Now, in this case, you don't have to do too much in terms of, the staring contest with the question, because, you will need to remember, okay, well, obviously these come into play in some capacity. We just talked about this, the antiderivative of secant x tangent x is secant. So if I'm going to create a u, and so that idea of u substitution, that's how important it is, I need it here. I want to define a u that will allow me to cancel out the secant x tangent x. That u should be equal to secant if that's the case. But that's not what this is. However, I do have a relationship. Secant squared, well, it's written in terms of theta, so I'll just leave it like that, minus 1 is equal to tangent squared. Or write it any way you want, but the idea is that's the relationship. If I were to take my Pythagorean relationship, 1 plus tcant, that's my name, tangent squared theta is equal to secant squared theta, and solve it for tangent squared, then I would get secant squared minus 1. All right. So there's a substitution. All right. So how is that helpful? Well, I can manipulate it. Well, that would mean that tangent to the fourth of theta would just be secant squared theta minus 1 squared. I'm just squaring both sides. That happens to be what I'm looking for here. So that tells me that I can replace tangent to the fourth of x with secant squared x minus 1 squared. So I have a new integral. And let me get rid of that underline because it looks like a fraction now. All right, so what I'm going to do is I'm going to let u equal secant of x, which means du is secant x tan x dx. The poor quality tan here, so I'm going to fix it. So clean substitution. du is going to replace all of this. Secant x tangent x dx. Well, actually in the next line. All right, so we're looking at, this is all gone. All of that replaced with just the du. And instead of secant squared minus 1, well, u is secant, so u squared minus 1. Distribute it out. U to the fourth minus 2u squared plus 1 du. Reverse power rule. 1/5 u to the fifth minus 2/3 u cubed plus u plus c. And then all I have to do is replace all my u's with secant x. And that monstrosity is my antiderivative. And honestly, I mean, for this kind of question, you need to know a process because, I mean, you're not guessing this. You know, you're not gonna just take a shot in the dark. Well, I know in some capacity it's going to involve a secant. So let me try 1/5 secant to the fifth of x minus 2/3 secant cubed of x plus secant x plus c. Or you're not even going to try a variation on that. Like, well, let me try secant to the fifth plus secant to the third plus secant plus c. All right, that didn't work, but it was only off by a constant multiple. All right, so let me try making it a 2/3. That didn't work. Let me try it a 1/3. You know, like that's not how it's going to work. You know, you got to know the process in order for this to play out. All right. So numbers 7 and 8 are along the same lines. I mean, number 8 involves cotangents, but it's the same skill. So I'm going to put a nice juicy star on both of those and let you try those for homework.